So welcome everybody to the last talk of the day. So our last speaker today is Yang Liu, and he's going to talk about sparsifying sums of norms. So take it away, Yang.
Yes, thank you, Dor, for the introduction, and I will be telling you about sparsifying sums of norms. So to start, let me just introduce the problem. In the sparsification problem that we're going to be studying in this talk, we're going to have functions f1 to fm, which are functions from Rn to R, let's say, non-negative. And let's define f of x to be sum over I in m. Right larger. Okay, sure. Yeah, so I have functions f1, and let's let the function f of x be the sum over I in m of fi of x. Okay. So this is the sum of these other functions that take Rn inputs and map to non-negative reals. And the general goal of sparsification is to essentially find a subset of these functions, reweight them, and show that we haven't changed the value of the sum by more than a 1 plus epsilon factor. More precisely, we're going to call a set of weights. Let me just make this definition, S epsilon sparsifier. I'm going to call a set of weights W1 to Wm. These are, once again, non-negative weights. We call these a S comma epsilon sparsifier if the following holds. The first is that the number of non-zeros among the weights W is at most S. And the second property is that if we define f tilde of x to be sum over I in m of Wi fi of x, then f of x minus f tilde of x at most epsilon times f of x for all x in Rn. So this is the goal, is to construct weights W which are a S comma epsilon sparsifier. And just to get some idea for the parameters that we're choosing in this talk, kind of here's like a dream or like a goal, is to show that maybe for some class of functions f, we'll study certain classes in this talk, for some class of functions f that we can, what's up?
Can you write a bit bigger?
Oh, okay, just in general. Okay, yeah, okay, I'll try. Huh?
In particular during the talk.
Yes, I understand. Okay. So a goal would be to achieve S and most, something like O tilde epsilon to the minus 2 times n. That would be a good goal to achieve in general. Okay. So you can't get this for all classes of functions, but I'll try to give some examples of functions where you can't achieve this. In general, sparsification has been very important in designing fast algorithms in graph theory and numerical linear algebra over the last 2 or 3 decades. So understanding functions where you can sparsify can lead to maybe further advances there. Let me just give some examples. Let me just give some examples of functions where it's known that we can sparsify. Let me start with some graph examples. In the cut sparsifier, this is generally defined as follows. Basically, here we should think of m as being the number of edges in the graph and n being the number of vertices. So we're going to define fi of x for x in Rv, where v is the vertex set. Fi of x is going to be absolute value xu minus xv, where you should think that I corresponds to the edge uv. Okay, and I guess you can also put a weight here, like maybe a weight r sub I. Okay. Now, another common definition is the spectral sparsifier, where here the function is not the absolute value anymore. It's instead Ri times the difference squared. And for both these settings, it's known how to achieve this dream goal. Now, beyond graphs, I'm going to call it like matrix settings or continuous settings.
in one is for all of Rn or just for like 0, 1,
Good. So the question, I guess, is for cut sparsifiers, you want it for all x and Rn or just all 0, 1? For spectral, it's normally defined that way. For cuts, it's normally defined as x being in 0, 1, but it's actually equivalent to this definition. The reason is that you can kind of like write for every vector x, again, write it as the sum without cancellation of the 0, 1s reweighted. So it's actually equivalent. Okay. So the matrix version, basically analog of cuts is what I'm going to call L1 sparsification. And here f of x is going to be the absolute value of ai dot x for some vector ai in Rn. The analog here is that ai would just be 1 sub u minus like 1 sub b. It's like the indicator of vertex u minus the indicator of vertex v. Okay, so it's more general. L2, as you might expect, it's ai dot x squared. Okay, and a little more recently, there's been people have studied generalizations of these notions. For example, what's been called hypergraph, like the hypergraph setting. So for hypergraph cuts, one way you can think of it as now for each I, we have a subset Si of V. And now Fi of X is going to be the max over UV in Si of XU minus XV. And similarly, in the spectral setting, you once again, if Si is a subset of V and Fi of X is the max over UV in Si of this time XU minus XV. It's just an analogy. I think it's if you try to, like for example, in graph settings, spectral sparsifiers generalize cut sparsifiers. So if you try to find a generalization of hypergraph cuts to hypergraph spectral, you kind of get the same thing. So that's where the definition comes from. So over the last 20 years, there's been a lot of work. Well, I guess even more than 20 years, there's been a lot of work on understanding, in fact, what is the smallest size of a sparsifier that you can achieve. Just to mention a couple, for the cut sparsifier, Benser-Karger showed that you can get n log n times epsilon to the minus 2. In this L1 case, which is actually more general than the cut sparsifier, but it'll be a little, yeah. So Talleyrand showed that you can also get n log n. For the L2 case, there's a lot of work, but the most, the best bound is due to BSS, Betzman, Spielman, Srivastava, which show that you can get n over epsilon squared without a logarithmic factor. So you actually don't need this O tilde for L2. Okay. Also for this cut and spectral case, there's been a lot of work over the last decade. I'm just going to mention a couple for this spectral case. There's work of Soma, Yoshida, Svensson, Trevisan, and then more recently, Kapralov, Krautgammer, Tardish, Yoshida. And then the authors of the paper I'm presenting today, I guess, Jampalapati, Liu, Sidford, and Lee. And the best bound known here is something like O of, best bound known here is something like n log R times epsilon to the minus 2, where R is the max over all I of the size of Si. It's the maximum size of any set. Okay. So this is just in general like a lot of things have been studied about sparsification. And to motivate the question I'm going to be talking about today, I want everyone to make the following observation. For every function that I've written down on this board, it's actually the power of some norm on Rn. Like this is like this is a norm, the norm. These are actually also norms because they're the max of the absolute value of some linear function. So the way you can think of this hypergraph setting is actually that it's a norm with the number of faces being like polynomial in this parameter R. So that's another way of thinking of the hypergraph setting. And in fact, all the proofs that work for at least the spectral setting exactly perfectly generalized to norms with R faces. Okay, good. So I guess in a pursuit to understand these settings better and to generalize the result, we're going to study the following question. What if we just let Fi be a general norm on Rn, and what can we say about that setting? Okay. So I'm going to change notation a bit just to clarify. So here, I'm going to let fi of x equal ni of x, where ni is a semi-norm on Rn. What is a semi-norm? Just to be completely clear, it satisfies two properties. If I scale by lambda, then I scale the value by lambda. And also it is convex. Or it satisfies the triangle inequality, I guess. Same as convexity because of the scaling property.
So you don't know colors?
Let me add a p here. That's better. Yeah. Let me add a p here. In the end, I'm going to take p equals 1 for most of it. So that's for all x, y in. Okay, good. And now I'm going to try to state the main theorem. To state the main theorem, I want you to find two properties of norms. The first I'm going to call the smoothness of a norm. We say that a norm is smooth for the power p if it satisfies the following inequality: ni x plus y to the p plus ni x minus y to the p over 2 is in most the sum of the pth powers. And the next is less important. I'm going to just the next property is equivalence. It's less important. We say that a norm n tilde is equivalent to the norm n if it satisfies the following: n tilde x is at least nx and most k times nx for all x in Rn. Sorry, one thing for smoothness, let me add a parameter here, s to the p, which is how smooth the norm is. I'm going to add a constant here. Now, given this, the main theorem, which I'm going to talk about for the remainder, is the following. If we have nx is the sum over I in m of ni of x, and n, this norm, let me add pth powers again, p, and n is s smooth with this parameter s here. I want to say it's k equivalent to an s smooth norm is k equivalent to an s smooth norm, then n admits an s comma epsilon sparsifier for s at most O tilde n times epsilon to the minus 2 times k to the 2p times s to the p. And let me add one more condition that p is between 1 and 2. Okay. So that's the main theorem. I guess I wanted to pause just for a second to try to make sure everyone understands the context and theorem statement before I continue.
So S is used twice. I guess it's clear from the context.
S is used twice. Good. I wanted this to be a capital S and this to be a lowercase s, but I suppose that's quite unclear in writing. For this most part, this S is going to go away for the rest of the talk. Like S and K will actually go away for the rest of the talk, so you don't have to worry too much about them. I'm just going to set them to be 1 for the rest of the talk, basically.
Maybe it makes sense to say that every norm is one smooth. So like if you think about p equals 1, then
yeah, exactly as James says. Yeah, for the rest of the talk, I was going to restrict to p equals 1, where in that case, notice if p equals 1, then every norm is 1 smooth with respect to p equals 1, and that's the case I was going to focus on for the rest of the talk. So, and also k would be 1 because I'm 1 equivalent to myself, which is a 1 smooth for p equals 1. So that's the case I was going to consider for the rest of the talk. Beyond that, were there any more questions about the theorem statement? There were no questions about the theorem statement. Then I'm going to describe one nice application before continuing. In the application, once again, I'm going to consider the p equals 1 case. So notice when p equals 1, every norm n is 1 equivalent to a 1 smooth norm. In particular, n is 1 smooth by the triangle inequality here. Okay. So that means any sum of norms can be sparsified down to size about n times epsilon to the -2 up to polylogarithmic factors. One application is in the area of like submodular sparsification. So imagine that each function fi of x is symmetric and submodular. Yeah, I'm going to define everything. Yeah. So assume every fi of x is symmetric submodular. This means the following. So I guess here, for this part, I'm going to briefly go back to the Boolean cube for if only a bit. So here, I'm going to let fi be functions from 0, 1 to the n to r at least 0. And we say that symmetric and submodular if the following properties are true. Fi of the empty set, I'm going to think of these as subsets, is 0. Symmetric means that fi of s equals fi of the complement set. And the third is the submodularity property, which is fi of s plus fi of t is at least fi s intersect t plus fi s union t for all st subsets of n. So this is submodularity, and this is symmetry, and the 0 is just for a nice normalizing condition. Then I claim that for any sum of these functions, it can be sparsified down to this size, because you can check that there exists a continuous extension of the fi's known as the Lovász extension. And for a symmetric submodular function, the Lovász extension is actually a semi-norm on Rn. To see this, you can actually notice that the Lovász extension of symmetric submodular function of x can be defined as follows: integral over r of I such that xi and most t dt. This is a definition of the Lovász extension of a symmetric submodular function, and you can check that it satisfies the properties of a norm.
There's going to be an s somewhere.
Yes, should clearly be fi of that. Okay, that's much better. No, this is really bad. Let me just call it f, not fi. That's better. Okay. And the reason that satisfies the norm properties is it's convex by the standard claim about Lovász extensions, that Lovász extensions are convex. If I scale x, then this exactly scales just by changing what t is in the integral. And if I negate x, then the value stays the same because of the symmetry property. So the Lovász extension is a semi-norm, and thus for any sum of symmetric submodular functions, I can sparsify it. Notice that this immediately generalizes like hypergraph cuts and things like that, because those are kind of the standard symmetric submodular functions. Okay, cool. Okay, so now for the remainder of the talk, I'm going to try to basically prove this theorem just in the case where p equals 1. That's like the simplest case, but has basically all of the main ideas. The way that most sparsifiers are constructed is via a random sampling procedure. And we can think of it as the following very simple algorithm. We call this sparsification by sampling. It's worth noting that the tight results that don't lose any logarithmic factors don't work this way, but I don't think it's really known how to do those in any settings other than L2. So sparsification by sampling is the following algorithm. We're going to define some probabilities P1 to PM, one for each function. And these are going to be in, I guess, 0, 1 probably, because they're probabilities. And now we're going to set Wi to be Pi inverse with probability Pi and 0 otherwise. And then basically the goal now is to define these probabilities P1 through PM, and then show that with high probability over Wi being chosen this way, that the result is actually a sparsifier. So how can we show that? Let's first understand the expectation of this sampling process, and then we're going to start studying the variance when we get into the proof. The expectation is not too hard. Basically, this process is exactly defined so that the expectation is that's unbiased for every x in particular. Let me just write here. N of x is the sum over I of ni of x, right? So the expectation of wi exactly equals 1. So if we define n tilde of x to be sum over I of wi times ni of x, then the expectation of what we want to be the sparsifier, n tilde x equals n of x. Okay, so it's correct in expectation. Now we want to understand the variance. Because the sampling is independent across the coordinates, we can calculate the variance as follows, or at least upper bounded as follows. The variance of n tilde of x is the most sum over I of nix squared times the variance of wi, right? Now, what is the variance of wi? Wi is pi inverse probability pi, 0 otherwise. So you can check that this is at most sum over I nix squared divided by pi. And I guess let me, for now, temporarily add this indicator that pi is not 1. If pi is 1, the variance is clearly 0. So I can always just add that there. But really, this is going to be the main term, the nix squared over pi. Now let me define one more term, which is kind of similar to the variance, but it's like the variance between 2 points x and y, not just x itself. I'm going to call this d. So I'm going to define d of xy to be the variance of n tilde x minus n tilde y to the 1/2 power, which you can check is in most square root over sum of I nix minus niy squared divided by pi. Okay. Cool. And I'm calling this a distance because we're going to eventually treat d as a metric when we go forth. Okay. So here I'm going to cheat a little bit and write something which is not actually true, but it's let's assume it's true for the rest of the talk. There's various ways to make it formal. Basically, what I'm going to try to say is the probability that n of x, n tilde x minus n tilde y deviates from its expectation is basically, it's going to be, the probability has Gaussian tails with this variance basically. So written formally, this claim is not actually true. There's various ways to basically make it true. The probability that n of n tilde x minus n tilde y minus nx minus n of y is greater than kappa times this variance term is the most x of minus kappa squared. Okay, so let me just try to describe what this is saying one more time. Recall that this is the probability over the weights W1 to Wm. So to describe what this is saying, recall that these terms are unbiased in expectation. So the expectation of this is 0. So now I'm saying that the probability that this term deviates from its expectation by more than kappa times the square root of its variance, claiming that it's sub-Gaussian. Okay. This is basically true because you're like independently sampling. It's not actually true, but there's various ways to make it true. Let's just assume that this is true. Now, given this, the next step is to apply something called Dudley's inequality to get the following here's the following main claim. The expected value over W1 to Wm of the max over all x with n of x and most 1 of n of x minus n tilde of x is at most integral over 0 to infinity square root log of the covering number of, okay, I'm going to write something and then I'm going to define everything. So here, Bn is the ball x such that n of x is n most, it's the unit ball of the norm n. So, and the covering number of a set in a distance d with delta equals the minimum number of balls of radius delta in this metric d needed to cover Bn. Written more algebraically, it's the smallest m such that there are points x1 to xm, and Bn is contained in the union of I is 1 to m of the ball of radius r around each of the radius delta around each of the xi's. Okay. Okay. So the goal, so this is basically a thing called Dudley's inequality, and it reduces bounding, it reduces whether n of x is a sparsifier to basically bounding these covering numbers. These covering numbers, once again, are, I have the norm ball. These are the set of points that I'm considering when I want to understand how to sparsify. I'm going to cover these by balls in the metric D. Let me just try to give us a little bit of an idea of why this holds.
Like the way that the norms are being, basically Dudley's inequality holds for any process that satisfies the claim.
Yes, that's a good, yeah. Dudley's inequality holds for any process that satisfies this claim above. The main point is that this square root log is like the inverse function of this x to the minus kappa squared. That's where it comes from. To give a little bit of an idea of where this comes from, basically, here's where this comes from. Let's say we want to understand for a fixed point x how to let's try to understand for a fixed point x whether this is true. So, okay, let's write a point x. Let's take a point x in Bn, right? And now let's let x0, x1 be a sequence of points. And let's say that xi, the distance between x and xi is at most something like 2 to the minus I. We're going to take a sequence of points that gets closer and closer to the point x. And we can write n of x as basically n of x0 plus this way. Yeah, what's up?
Yeah, I have a possibly silly question.
Mhm.
So what if n tilde is plus like some gigantic number, say like a billion?
Okay.
Then it seems like this max quantity could be arbitrarily large, but you still satisfy the tail bound in the claim.
You know, there's an expectation.
Not sure I got that.
So if n tilde, I mean, so n tilde equals n in expectation, right?
Oh, equals, okay.
It's an unbiased estimate.
Cool.
It's an unbiased estimate. Yeah, that's critical. Yeah. That's because of how these sampling weights are defined. So everything is correct in expectation, and the goal is just to bound the tails in all cases.
Cool, thanks.
to get an idea of where this holds, I'm not going to say too much about it, but the basic idea behind the proof is to write n of x as the following, basically telescoping series. So now, if you wanted to bound this an expectation, it suffices to bound each of these terms separately, right? Now, for each of these terms here, notice that, well, basically what's going to happen is x0 is going to come from a discrete set that is represented by this covering number. X0 is going to be like a point that is going to be a point that's the center of one of these balls. X1 is 2. So each of these is going to be like a finite number of objects that we need to bound. And because we have this tail, then you'll bound each of these by a turnoff bound, and then it telescopes out basically. And the integral is just going over different levels of scale. That's basically where that's coming from.
Square log is the inverse of x to the minus square.
Yes, that's right. Yeah. It's to like, yeah, it's basically if you like what turnoff says on each of these separate things, and then you integrate, it's like kind of you're summing over each of the terms.
Not Chernoff, the claim.
Sorry, the claim, not turnoff, my fault. Yeah, it's the claim. Yeah, it's because of the claim and the inverse there. Okay, cool. Okay, so for the remainder of the talk, I'm going to describe how to pick the probabilities pi and how to bound the covering numbers. So to start, let me define what the probabilities pi are. Defining PIs. So here's how the PIs will be defined. I'm going to define the following measure, mu on Rn. So mu here is proportional to e to the minus n of x. This is a log concave distribution on Rn. And we're going to define Pi to be the expectation of x from mu of ni of x, and then times rho. Rho is going to be some oversampling parameter. And in the end, we're going to pick rho to be, basically, it's going to be log to the 1.5, I guess maybe 3.5. It's not going to be, it's going to be something like this. We don't need to worry too much about what it is now. We're going to just decide it at the end. Okay. I want to compare this a little bit to how sparsification for other settings works, just to give an idea.
These don't sum to 1.
Oh,
they need to sum to 1. Okay.
Yeah, they don't say. Just as a point of comparison to L2, in L2, what ends up happening is you actually pick Pi to be the following. So L2 is, remember that Fi of x is AI dot x squared. Here, Pi is going to be AI transpose M inverse AI, and then also times this rho, where here M is this total matrix, sum over I. Another way to, yeah, so that's just a point of comparison.
I guess these PIs aren't necessarily less than 1, but you just take the max of the minimum of this in 1.
Yeah. Let's not worry too much about these points. So as James says, PIs might be greater than 1, but let's not worry too much about that. Let's just say they're like less than 1. It makes things a little easier. Okay. So now, given these PIs, let me state the main covering number bound. Lemma. So the covering number of Bn by D with delta is going to be at most x of going to be a log to the 1.5 of m, and then times 1 over rho times 1 over delta squared. Now, let me try to use that to conclude the proof first before showing it, basically. concluding, let me call this like lemma 1 or something. To conclude from lemma 1, we're just going to apply Dudley. And if you apply Dudley, then what do you get? Well, you get that the error there, we call that the, let me just write it like expected value of max over nx and most 1, n of x minus n tilde of x, and the most integral square root log of that. So square root of log to the 1.5 m over rho times 1 over delta squared. 1 over delta times square root log to the 1.5 m over rho. So you might be a little worried here now because this integral does not converge for 0, delta being 0 and infinity. But it's a standard thing that happens in these Dudley integrals, that really what you're supposed to do is in this integral, you break it into a few parts. You break it, how do I want to write this? Basically what happens is the integral breaks into a few parts. There's the part where delta is less than 1 over poly m. There's the part where it's greater than poly m. And those parts, in general, they're negligible. They contribute a small amount. And the only parts that are critical are between these two. So then you get it's in most log m times log to the 1.5 m over rho. So for the choice, as we said, rho is log to the 3.5 m over epsilon squared. Then this is n most O of epsilon. And that completes the proof. Okay. So yeah, for the rest of the talk, I guess, the main goal will be to show this covering number bound. Okay. Were there any questions before I go into that last part of the talk? Yeah.
Like those parts that you threw out of the integral, you have better covering numbers?
That's correct, yeah. Okay, good. Yeah, so I guess the question was, in the parts I threw out from the integral, do I have better covering numbers? And the answer is yes. The reason mainly is because, I guess I wrote this, right? You can also show the much easier covering number bound, Bn d epsilon is in most something like O of 1 over delta to the power n. This is just, or like maybe n or m or something, like I think n, maybe m. And the reason is because you can kind of just look at each function in the sum and just discretize it by delta over m or something like that. And this is much better than this bound if delta is 1 over poly m. So then if you plug this in to deal with the small parts, then you're done. And for the large parts, basically the covering number is 0. So that's why they go away.
Maybe you said that already, but then that ball of all the axes for which n of x is at most 1.
That's right.
How big is its radius measured according to d?
Yeah, good. That's a good question. How large is its radius measured to d? It's basically going to be n most 1.
Okay.
Yeah, but I guess you're gonna have to.
So that means that when delta is more than 1, the covering number becomes 1. And
it's 1, and then it's yeah, exactly, yeah. But to see that, I'm gonna have you kind of have to go through most of this proof, or like some amount of that proof. So,
oh, it's not something that just comes from the definitions.
No, it comes from the definition of the PI, but like to see why the covering number becomes 1, you actually have to kind of walk through the proof of this already. So, unless James has it easier.
No, I'm just saying that the bound on the covering number, like that generally speaking, that would be false. The one the simple one you wrote down.
This one.
Yeah, because you have to. Like, you kind of wrote it like it's a trivial thing, but I don't think it.
So you need to know this fact that the radius of the ball is 1 according to this.
Oh, okay. You might be right. Yeah. But I'm not going to go too much into that. Obviously, happy to go through details. Okay. Okay. Let me try to walk through this covering number bound for the rest of the talk. the way that the basic way this covering number bound works is, so let's think about what the goal is. We want to show that we can cover this Bn with balls in the radius d. So by packing covering duality, it basically suffices to understand what's the largest number of balls that I can pack into Bn that are diameter, like radius about delta over 2 or delta over 4 in D. So here's Bn, let's say. And we went to, we have a bunch of balls that we want to pack inside. And let's say the radii are like delta over 2. Then if you were to scale up each of these, if these were maximal and I was to scale up each of the balls by a factor of a constant, then I end up covering everything. This is packing cover duality. So it suffices to understand what's the maximum number of balls that I can pack inside. And the basic idea behind this proof is something called the Sudakov method, where you basically understand what is the measure of each of these disjoint balls under some measure. The measure that we're going to use is basically this log concave measure here. And then because the total measure is at most 1, that gives you a bound on the total number of balls. So let's try to execute this proof now. To execute this proof, let me define a slightly different measure, mu lambda, which is going to be proportional to e to the minus lambda n of x, where I'm going to choose lambda a little later. Well, I guess I'll just write down what it is now. Yeah, it's going to be log to the 1.5 m, and then times delta to the minus 2 times 1 over rho, I guess. Okay. E to the lambda, I mean, mu lambda is going to be proportional to here. And we're going to try to understand what is the measure of each of these balls in under mu lambda. Okay. So to complete the proof, well, let me write k. So k is going to be, I need to do one thing before this. Okay. I guess before starting, I need to do one more thing, which is to simplify the distance d, which, did I erase the distance d? Huh? It was here. Okay, that's not good. Okay, so I guess let me rewrite what d was, which is the square root of the sum over I of nix minus niy squared over pi. The first step is going to be to simplify this d, or to upper bound it. And to upper bound it, we're going to just write its most sum over of nix minus y times nix plus niy over pi. So then most sum I in m max I in m and I x minus y over pi sum nix plus niy, which is then most square root max I in m square root of nx plus ny. Okay, so now if x and y are inside this ball Bn that I've defined, then this is just in most up to constants, square root max I in m nix minus y over pi. Okay, so this is going to be kind of the new distance that I'm actually going to use. I'm not going to really deal with this old one because it's more complicated. But inside this ball Bn that I'm considering, this is the important distance. It's square root of the max of the ratio of the norm I between x and y divided by pi. Okay. Still here. Now to continue, let's define the body K to be basically the set of points around the origin that's small with respect to that distance. So we call this distance d bar of xy. So K is going to be the points x such that the max over I of nix over pi is in most delta squared. So I guess that means the square root is in most delta. Now, the proof will follow from the following two claims, the first of which I will defer to the end, and the second of which is easier. The first is that for this choice of lambda, then mu lambda of k is at least 1/2. That the measure of this centered set is at least 1/2. This will follow from basically concentration of log concave distributions in the KLS conjecture results. And the second lemma is that for any xi with, I should write xi in Bn, any xi in the norm ball, then mu lambda of the ball in d bar around xi of radius delta, which is as defined exactly equals mu lambda of xi plus k, is at least 1/2 e to the minus lambda. Okay. Let's see the proof of this first. You can see that mu lambda of xi plus k, this shifted ball over the original, is the following: integral y in k e to the minus lambda n of xi plus y divided by integral y in k y. Why? Because this is the definition of mu lambda over there. Okay, now by the triangle inequality on the numerator, this is going to be at least e to the minus lambda n of xi, which is e to the minus lambda. And then combining this sequence of inequalities with the above claim gives the result. At least is correct.
Yeah, but you talk about the measure of Bn itself.
At most one. It's going to be at most one. Yeah. The measure of Bn is at most one because it's it's a measure.
Oh, just because.
Yeah, I'm defining everything to be a measure. Yeah. Okay. So now, let me now finish the proof of lemma 1. Okay. So now let's say that x1, xm are such that d bar xi delta are disjoint. Then clearly, sum of mu lambda b d bar xi delta is at most 1. Well, I guess it's at most, mu lambda of Rn is at most 1. So that means m is at most 2 e to the lambda. And for the choice of lambda that we made, it's fine. Okay. So I guess the last part now will be to understand this claim that the mass mu lambda of k is at least 1/2. Let me do it. So remember what k is. K is exactly defined as the points x, where ni of x over the pi's is at most delta squared, right? Okay. So it suffices to show that the probability of x from mu lambda that nix over pi is greater than delta squared, show that this is the most 1 over 2m, and then we can union bound over each of the i's. Okay, we're going to show this and then union bound over each of the i's. Recall what pi is. Pi is expectation of x from mu, which is a slightly different distribution of ni of x. Okay. Good. Okay. So I guess times rho. Okay. So this is probability x from mu lambda nix greater than delta squared rho expectation x in mu ni. Okay. Now let me get rid of this kind of x from mu lambda. So remember what mu lambda is. Mu lambda is like e to the minus lambda n of x. So if we just scale x, then we can change this to x from mu and put a lambda on the right hand side here. These are equal. Okay. Good. So now by the definition of lambda, then this is exactly probability x in mu nix greater than log, I guess, c times log to the 1.5 n expectation x in mu. What is this saying? This is asking for what the probability is that a norm that, so ni, remember, is a norm on Rn, and mu is this log concave distribution. So this is asking what is the probability that ni of x is greater than polylog factors times its expectation under mu. So this is basically exactly what the recent progress on the KLS conjecture tells us is small. A little more formally, the progress on the KLS conjecture tells us that Lipschitz functions have sub-exponential tails under log concave distributions. Okay, so okay, yeah, let me just try to formally state what's going on here. So I want to show that this is at most 1 over 2m. We're going to require the following theorem. So let phi of n be the KLS constant on Rn. Then for any L Lipschitz function, Lipschitz under the Euclidean norm, for any L Lipschitz function f and isotropic log concave distribution mu, we have the probability that f of x minus expectation f of x greater than L is greater than t is going to be at most e to the minus t over L phi of n, then times the constant c here. Okay. This is due to like Romanov. It says that, yeah, for any L Lipschitz function f, the probability over x in mu that f is greater than its expectation is exponentially decaying, where psi is the KLS constant. And recently it's been shown that this is n most root log n due to Klartag, though there was a long sequence of works, Lieb and Pala, I guess Eldon maybe, Lieb and Pala, Chen, Klartag, Lehek, that steadily improved the bound. Okay. 5 minutes, okay, yeah, this is, okay. So now, basically, I'm just going to bound the Lipschitz constant of the norms and we will be done. That's correct, yes. The mu is not isotropic yet, but it's fortunately not a big deal. So I wanted to bound this where mu is some log concave distribution, we can assume that it's isotropic because you can just do a linear transformation. It doesn't affect the statement at all. Okay. So now we want to understand what is the Lipschitz constant of a norm nx. So Lipschitzness ni. Ni of x minus y of x minus ni of y is at most ni of x minus y. So it suffices to show that ni is Lipschitz. It suffices to check that ni of x is at most some L times x2 norm for all x in Rn. So write ni of x to be max over y in the dual norm of y dot x. And by Cauchy-Schwarz, this is at most x2 norm times the max over y in n star of the L2 norm of y. Okay. Now, okay, so then basically this is an upper bound of the Lipschitz constant. Now we want to compare this to the expectation to conclude the proof. Now, notice that the expectation of x from mu of ni of x is at least expectation x in mu of y star dot x absolute value, where here y star is the argmax, y in n star of y2 norm. Okay, and for log concave distributions, all the moments are the same up to constants. So you can put a square here, 1/2, and then this is x in mu y star transpose x transpose y to the 1/2. Because this is isotropic, this exactly equals y star 2 norm. Okay, so that means that the Lipschitz constant is at most the expectation, and that completes the bound there. Okay. Yeah.
Transformation.
You shouldn't think of it that way. You should think that I've transformed the norm ni into like a new norm. Does that make sense? Like,
So if you want to prove this for every norm,
maybe think of it this way. Like instead, think of it as like ni of ax greater than c log to the 1.5 m. Expectation ni of ax, where a is like the covariance matrix of mu. And then the ni I wrote over there is actually ni of a, which is a norm on Rn still.
Then then going up on the ni with the operator norm of a my cup or I see.
So like the ni I wrote over there is actually ni of a of x. Like it's a composed thing. Yeah. And I guess sorry. There's one thing that I kind of forgot to mention the whole time, which is I never actually bounded the total size of the sparsifier, but that's not too difficult. So I'll be done right after this. And as the final point, to bound the total size, because I'm sampling with probability p, the total size is at most the sum of the pi's. And the sum of the pi's is the expectation of the sum of ni of x, where x is from mu, which is the expectation of n of x, where x is from mu, and mu is proportional to e to the minus n of x. And it's a nice calculation that the expectation of x from mu, where mu is this, proportional to this, is actually exactly equal to n. And sorry, pi is rho times this by default, rho n. And because we chose rho to be O tilde of 1 over epsilon squared, that completes the proof. Okay. So I think, yeah, that's all I had, and thank you.
Questions for Yang?
You can implement this efficiently, like is this important in application?
So you can, in principle, implement it in polynomial time by sampling from the log concave distribution. In fact, if you care, you can also get in like what people call input sparsity, which means that the runtime is m plus polynomial in n, and where m it means like m accesses to the norms ni.
Can you comment a bit about how you do it for squares? Squares of norms.
Oh, so like good. Sums of squares of norms. Good.
Is it like, does it kind of recover effective resistance?
Good. That's a good question. So for sums of squares of norms, basically the probabilities pi are exactly what you expect. You would set up mu is e to the minus n of x squared, and then the pi's are expectation of ni of x squared. And if you write that down, that's exactly the same as effective resistances. However, it's not, we don't know how to show that if you do that, then the size will be all the way down to like you can get size n over epsilon squared with that. Yeah, we don't know how to show that. We only know how to show it with this additional smoothness assumption, which ai dot x squared does satisfy, but possibly like higher dimensional norms don't.
Do you want to mention that as that open question?
Yeah, good, okay. Yeah, okay, yeah. I guess I ran out of time, but that would be a good open question. Which is, so let's say we have n of x squared is sum over I in m of ni of x squared, where we have no smoothness assumption on the ni at all. These are just arbitrary norms. Then what is the best sparsity? Best sparsity. In general, if you replace these with p's, we can show a bound of O tilde n to the 2 minus 1 over p times epsilon to the minus 2. So it's like n to the 3 halves for p equals 2, but we don't know whether anything better is achievable.
And this isn't for p larger than 2.
For p larger than 2, I guess you got, yeah, you can also, we also don't know the right bound.
Yeah, okay.
It's not going to be linear. Yeah, for p larger than 2, you can never get a linear size in general, even when they're all 1D like ai dot x. So that's why I didn't talk about it too much. Anyway, I would be happy to discuss afterwards if people want.
Okay, no more questions. Let's thank you again. We'll see you tomorrow for the final day.